For those of you that may not know, I am Justin Noel. I work for a Qt consulting outfit called Integrated Computer Solutions, otherwise known as ICS. We primarily work out of North America. We are the largest Qt partner in North America. We also do all the training for Nokia on Qt in North America. So us at ICS, we do a lot of consulting, and we also teach a lot of training classes. The tips and tricks that you'll be seeing today are actually derived from our years of experience in consulting. What's going to happen is that this is a collection of, depending on how you count, between 20 and 30 good ideas, interesting features in Qt that you can use, and pitfalls to avoid. These notes are set up to be reference material. So there's a lot of code that's inlined inside of the notes. You're going to see a lot of material today. You're going to see some interesting things, and you're probably not going to remember them when you get back to your office and you get started in using model view controller or cross-thread signals and slots. But if you drop by the ICS booth and hand in your business card, I can make sure that you get a copy of these notes as soon as possible. Otherwise, you're going to have to wait for the videos to come out on Nokia's website. So without further ado, let's go ahead and check out some of the topics. These tips and tricks I've loosely grouped into topics, such as we're going to talk about meta objects and what they are. Qt has a design. When you use the QObject class, you get some generated code that comes along with your class that is generated by the meta object compiler, and it has lots of interesting information about your classes. You can sort of think of this as Java introspection, except in C++. We'll talk about QVariant, which is a meta type, and we'll talk about implicit sharing, which is how you can save memory by having data classes not be copies of each other, but be reference-counted pointers to each other. We'll talk about some pitfalls when using model view controller in Qt, and we'll talk about things with performance, how to make your applications faster. Then we'll move into some threading tips, miscellaneous grab bag, and finally, some things where Qt can help you test your application. So the first tip is with the meta object system, using Qt properties. Some of you may have seen this macro when you've been working on widgets, when you've been, say, reading the Qt source code. The question is, what does this do? Well, the idea is that you can take functions that you've already written. Generally, you'll have a member variable and a getter and setter for that property of your class. What happens is that Qt can go ahead and take that setter and getter function and encode that into the meta object file so that you can generically set and get that property. This is exactly how Qt Designer figures out all the properties of the widgets in the Property Explorer. So when you declare a property right after the QObject macro, you can use the QProperty macro. And you give it a type, like int or an enum or string, could even be your own types, a name, a read function, a write function, and possibly a reset function. Maybe you want it to be seen in Designer. Maybe you want this to be scriptable. These are some options that you can pass so that the meta objects have the right information in them. So I mentioned you can use your own types as properties, so that in your property declaration, you can have, say, my class instead of any of the C++ primitives. And you can do this by making a class that is QVariant compatible. Out of the box, QVariant can support storing all the C++ primitives and most classes from Qt, like rectangles and pixmaps. To declare your own meta types, you simply just need to define a class and use a macro called QDeclareMetatype, which is going to expand into code. And then you need to call a special function as the template called registerMetatype. You can also use enums with your properties. And what Qt is actually going to do when you tell Qt that there's a property that's an enum, it is automatically going to make string integer mappings for that enum. So when you ask Qt to save things to the disk, such as design or UI files, it's not going to save the integer value. It saves the string value. So what this means is that your file format will still work even if someone changes the enum. So here's an example here of making a property. We have a very simple widget. It has a title property. It has a title function, set title function, and clear title function. And we simply give these to the QProperty macro, and the meta object compiler is going to do all the magic. So when you use QProperties, you get the ability to have to use your class in Designer and have Designer figure out all your properties. You get the ability to export your QObject into QtScript or into QtQuick and have all your slot functions be callable. Have all your properties be values that you can set on your exported objects. There is also on QObject a generic set property and get property. You can also get a list of properties. This is a very easy way to generically save and restore property values. Another interesting trick that you can do with meta objects, not only is it recording all of the properties of your class, but for signals and slots to work, it's also recording all the signals and all the slots. Now, if you've looked into how signals and slots work, basically it's dynamic function calling. And the same function that Qt uses to execute your slots, you can simply call yourself. It's called invoke method. It's static. And you can invoke any slot. You can invoke it synchronously or asynchronously. You can get to pass parameters and get a return type out of it. Of course, if you execute your function asynchronously, you're not going to get the return type back. It's very useful to some people who have done quick hacks with QTimer single shots, except with invoke method, you can pass parameters, which is very important. You can also use invoke method to create IPC mechanisms. Let's say you've got a network packet that says, I want to run this function, and the function name is a string. You can actually give that string to invoke method, and the meta object system will go ahead and invoke that function by name. You'll see the constructor, the function call here. The signature is it's a static method. It takes a QObject pointer. That's the object you want to execute the function on. The name of the function you want to execute, and a connection type, whether you want it to basically be direct and synchronous, or queued, which is asynchronous. Likewise, you can pass it arguments and return types. There are macros that are going to help you build the return types and be type safe. Like here, there's the QArg macro. You have to pass it in the type that you want to pass, and then you get to pass a value. So if you wanted to execute something synchronously, you could here just say, invoke method on object, do stuff. And that will happen immediately. As soon as that function returns, that slot has been called. Or you can decide to process this asynchronously. What's going to happen is it's going to post an event to the event loop for that object, and it will get processed later. You might do this to send messages to other threads, because each thread can have their own event loop. This is exactly how cross-thread signals and slots are implemented by Nokia, and this is all public API that you can use. So we'll move on to talking about QVariant. We talked about how there's this meta type that allows you to save and restore generic things from QProperty, and it's based on a variant type. Basically, this is a template class that is going to hold what I would call a glorified void star to your type, and it remembers the type and is able to convert it back and forth from variant type to your type. Out of the box, all of the C++ primitive types are compatible with QVariant. Most Qt data types also are compatible, such as QRect, QPixMap, QString, and so on. You can also use your own custom types. Like I said, we talked about using QDeclare metatype and register metatype, and we'll see exactly how that works right now. Now, these variants are used in a lot of places in Qt. You're going to see them used in scripting, in model view controller framework. You've already seen them used in properties, and you also need to be Q variant compatible to be used in cross-thread signals and slots. So with these one macro and one function call, you can register your own type with variants. So here's an example of a car class. The car class is very simple. It has a make, a model, and a couple of get functions. In the declaration, immediately after, we simply say QDeclare metatype and give it our type name. This is going to expand into a lot of template code that is going to handle converting your type to QVariant and converting it back from QVariant. Then somewhere in your code, it could be anywhere before you use this type with QVariant, simply call the template function QRegisterMetatype. And what that is going to do is going to allow copying of your type when you use it with properties, or copying when it comes to passing it across event loops. So there are some pitfalls that you'll run into as soon as you start using your own types with QVariant. Some things just stop working. An example of this is that there's a function called type that's very useful. It returns an enum type for what is located inside of the variant. Unfortunately, the enum is limited and not expandable. So any of your types do not appear in this enum. To check for your type, you need to use these template methods, such as here you can see canConvert. That is going to tell you whether or not this variant contains your type. Then you can use QVariantCast, which you can think of like a dynamic cast. It will return an invalid type if it fails, and this will convert from the variant to your custom class. Also, when you use your own custom types with QVariant, the comparison functions no longer work. For native types and Qt types, you can say if variant equals some other variant, equality operator, do something. That no longer works with your standard types. You're going to have to convert them back to your type and compare them yourselves. However, something that does work very well is integration with QDataStream. You want to serialize your object, maybe out to a file that's binary, maybe off across the network. And what you can do is you can simply implement QDataStream operators that have this particular function signature, and use QRegisterMetatype stream operators. And what this is going to do is it's going to register your serialization methods with the variant system. So something that is not so much related to variants, but are really interesting things in Qt are implicitly shared classes. Who here knows what implicitly shared classes are? Raise your hand. OK, so I see there are a few hands not up. What implicitly shared classes are is you have like QString, for example. Could have a very long string inside of it. However, copying QString is very fast, you may have noticed. Because what happens internally is that there is a pointer to data and a reference count. And when you copy a QString, you're simply making a copy of the pointer value and incrementing a reference count. So those two copies of QString will have a pointer to the exact same data. It is only when you go to manipulate the data and change it that there will be a copy made. A function called detach is called, and now that copy will have its own data and no longer related to the class you copied from. So what that will allow you to do is it will allow you to save on memory, because you can use the same string over and over again and not have to make actual copies. And it makes copying things very fast, especially if you're working with iterators and want to dereference them into their actual types. If you're implicitly shared, there's almost no penalty for dereferencing a pointer and copying it. An iterator, I should say. So a lot of things in Qt, all the heavyweight data classes implement this. This includes QImage, QPixMap, QString, QByteArray, many classes. And in fact, as part of the public API, Nokia allows you to go ahead and use implicit sharing in your own classes. So if you have a large chunks of data that you need to pass around by value, it can speed you up quite a bit. So the first thing you need to do is inherit from QSharedData. And this is actually a very simple class that implements atomic reference counting. And the atomic part is very important, because QSharedData is thread safe. This means that you can increment and decrement the reference count such that another thread isn't going to also stomp on the reference count while you're modifying it. So QSharedData simply provides a ref and a deref function, but they have very interesting implementations. I wouldn't suggest implementing your own. Then there's another class called QSharedDataPointer. And what this template class wants is it wants something that inherits from QSharedData, because it wants to use that ref and deref to reference count a pointer. And what you usually want to do is you want to wrap this all in your own class and hide this from the user. The user should never know that you're using QSharedData or that you are using QSharedPointer. Just like in Qt, this should all happen behind the scenes. So here's an example of a employee data. This is pretend it's a heavyweight piece of data. It's really got nothing in it right now other than a string and a name. And the string is already implicitly shared. And we simply go ahead and inherit from QSharedData. It gives us ref and deref. Don't have to implement that. Implement your class just as you normally would. And then you create your wrapper. Here we call it employee. And what this is going to do is going to be the wrapper API for employee data. And employee data here is wrapped in a QSharedData pointer. And what this is going to do is that any time that we modify that private variable d, it is going to go ahead and detach and actually make a copy. However, in our copy constructor, what happens is that we just say that pointer is equal to the pointer that we're being copied from. So the trolls are very good at implementing really interesting features and then exposing them so that you yourself can use the same systems. We've seen that with invoke method. We now see it with implicitly shared classes. So now I'd like to move on to some model view tips. When we're consulting or doing training, we often get a lot of questions about how to properly implement model views such that it's efficient, it's fast, and works as designed. So a rule of thumb that I usually go by, I'm a very big model view design pattern fan, is that you should avoid using the widget versions of the lists and tables and trees. You should only use them for very simple things, like if you had a list of things and you wanted the user to pick one of them, or maybe a list of fonts. It would be acceptable to use either the widget version of, say, QListWidget, or to use a QStandardItem model along with a list view. The reason why these aren't generally good ideas is because they need a copy of the data. So if you have a data structure that is, say, an address book that has groups and contacts, well, that's a tree. You have groups on the top level and contacts underneath that. If you wanted to display that as a tree in a tree widget, you would have to copy all that data into the widget or into the standard item model, and then keep it in sync with your address book class. The better solution for this is to implement your own QAbstractItem model, which from here on in will be acronymed to QAIM, QAbstractItem model. So you're going to use this as an interface class to your actual data. So your actual address book would be the data storage mechanism, and the abstract item model would just be a wrapper. And then the Qt view just sees it as a data model. It doesn't see anything different from that or the standard item model. When you implement your own model, there's some things you need to be aware of. The first is this class called QModelIndex. It is a representation of a cell in pretty much XY coordinates, row and column. But it also has another dimension called parent. And this allows you to make a tree. So in QAbstractItemModel, there's an index function. It takes in a row, a column, and a parent index. Now, this is for views to call in your model to navigate. So if they want a particular cell, they're going to call index. And these indexes are passed all throughout the Abstract Model API. Now, the internal implementation is not int another model index. That would just get data bloat out of control if you had a large tree. What it actually is, it's a row, a column, and an identifier. Your identifier can be a 32-bit integer, or it can be a void star pointer. Now, the void star pointer becomes interesting because now you have a hunk of client data that you can embed into your cell identifier to directly access your data. It is very small and very fast, but it can be slightly dangerous. Q-model indexes are transient objects. Once you ask the index function to provide one of these, you are to use it immediately and never store it. Because if there are any inserts or removes, that model index will become invalid, but you'll never know it. You'll simply be accessing bad data, or even worse, pointers that don't exist anymore. There is a solution for this, though. Should you need to store Q-model indices, maybe you're making a proxy model that does mapping, maybe you're making something that is going to associate your model with actual widgets on the screen, you can use a Q-persistent model index. And this is actually a model index that can be stored. The row, column, and internal pointer are actually going to be maintained by the data model. This means for every insert, these are going to be updated. So if you make 1 million of them, you're going to spend a lot of time updating persistent model indexes. So you should watch out for that. But they are very useful if you need to do mappings where you need to store things. Now, some people look at the documentation for QAbstractItemModel and become very scared because there's a lot of functions in there. But there's not so many that are pure virtual. You can actually get easily started on a table model by subclassing QAbstractTableModel. Takes care of that parenting stuff for you because that doesn't exist in tables. And all you need to implement is row count, column count, and the data function, which takes in an index and a role. So you might say, well, why does data need basically a cell identifier and a role? Well, the roles allow cells to return many different pieces of data. So you can think of it like a third dimension. You could return a pix map, and that's called a decoration role. You can return a string, and that's called the display role. You can even have a different string for editing, and think about that like Excel. When you edit fields in Excel that have formulas, you don't edit the value, you edit the formula. So this is basically a third dimension. And it's passed as an int rather than an enum to make it much easier for you to implement your own custom roles. So if you're doing advanced model view stuff, you could have very deep cells with a lot of data. So for a read-only table, it's 3 functions. It's not as difficult as it looks. For editable tables, it's 3 more functions. You need to provide set data, insert rows, and remove rows. And you'll notice that throughout this entire API are these Q model indices. It's pretty much what powers the QAbstractItemModel. Also, when you set data and get data, you're passing in and out Q variants, another place where Qt is using a generic type that you can extend. So trees are a little more difficult because you need to implement your own parent function and your own index function. Trees can get a little hairy, but it's well worth the effort, especially if you're making something like the address book, where you have data that's already a tree. There's no reason to copy the data and then worry about resyncing it anytime something changes on the screen. So I'm about to show you an example of wrapping a tree, or a data structure that's a tree, with QAbstractItemModel. And what we're actually going to wrap is a Q widget, because a Q widget is a tree. It has children widgets, and those widgets have child widgets, and you basically have a tree. And this is an actual example program that is taking a hunk of widgets from Qt. And this view is using a custom model to display the widget hierarchy as a tree. And this is going to show you some more meta object tricks, because all the strings it's getting, like class name, object name, those things are coming from the meta objects. That is things recorded by the meta object compiler and built into your classes, so you can ask them, what's the string name of your class? What's the object instance name of your class? So I'm going to break out of the notes for a second, and we're going to go ahead and take a look at this in detail. We'll notice here that this is a tree model, and we've implemented a number of functions. And we needed data, row count, column count, index, and parent. The rest of this is going to help us maintain our objects so that we can map an object, QObject pointer, to a model index, because we need to associate the model index with the data that it represents. And the way that this example works is that the void star pointer that we're going to use to identify the objects, we use the object's parent. And you can see here that in raw lines of code, we have about 113 of them. And we got all this functionality. We got to see all the widgets in the hierarchy. So let's take a look at how this is done. So this is a object browser model. It implements QAbstractItem model and takes in a QObject to be what it's going to show for the tree. And we record some information about the root item and the parent of the root item. And the magic behind this model is going to be the mapper functions. The first is going to map a QModel index to the QObject that it represents. And this is pretty easy because we can cast the internal pointer to a QObject. And because we've embedded the parent of our QObject as the void star pointer, we can then query its children and get the QObject that this cell represents. Likewise, we need a function that is going to give us all of the children for a particular QObject. This is going to allow us to build the subtables of the tree. Column count is really easy. We simply define that to be 3. Row count, for each model index of the tree, we are asked to give a row count for each subtree as you go along from node to node. So here we basically look up the object associated with this cell and find out how many children it has. Pretty easy. Data goes ahead, and we simply use our mapper function to map an index to an object. And then we use things from the meta objects, such as object name and class name, to return strings that we are going to use for the display role. And index is pretty easy. All we do is we create an index with a row, a column, and then a pointer to the parent of the QObject that this row is going to represent. The real hairy part comes up when implementing parent. It looks short, but you've got to cover 3 different things. First, you've got to cover when you're passed in an invalid index, then that index should be invalid that's returned. If you return a top-level item, you should also return an invalid index. And finally, for actual child indexes, you use create index. So in not a whole lot of code, we have created something that has wrapped a native data structure and provided us a tree. So this could have been done with the standard item model and copied all of these strings for class name and the pointer number and the object name, but we would have had all this extra code. So going back to the notes, we are going to have a look at our next topic, which is using QStyle to either implement your own custom widgets or to implement delegates for the model view system. what a delegate is it is the class that has been delegated the authority of rendering and editing cells. And sometimes when you want to paint cells, you don't want to paint strings. Maybe you'd want to paint progress bars. And the question is, well, how do I make a progress bar inside of my table that looks like a real progress bar? But I have 1,000,000 rows, and I can't make 1,000,000 progress bars. That would be an entire waste of memory. How would I go about doing that? Well, you could take the item delegate and subclass and re-implement paint. And inside of paint, you can ask the QStyle engine to draw you widgets. The QStyle engine is not based on QWidget. It is based on QPainters. So it can paint you widgets anywhere you want. You could even paint widgets to pix maps. So, like for example, you could have implemented this slider spin box, which is an actual hunk of code that I put together. And it shows how you can create elements of both a combo box and the progress bar to create a new widget that you can visually see what the value is by just scanning the screen. So we're going to take a look at the source code to another class that I wrote called the QICS tree combo box. If you want a tree in a combo box, you can't actually do it with QComboBox. The API really doesn't support it. So I made another widget with a similar API, and I asked QStyle to draw me what looks like a combo box, so that it will draw me the exact look and feel of a combo box on any platform. And it's actually really easy, because you just need to make this data structure called an option. And there's actually an option usually for each type of widget. So here it's QStyle option combo box. And this has a lot of public members in it that I cut out of here, such as font and text and current index and font. Everything you need to know to actually draw a widget. So once you have this, you can use something called a QStyle painter. And this works on any QPaint device. This is a widget. This is a QPrinter, piece of paper in the printer, an image, a pix map. Anything like that can be used with QPainter. Likewise, QStyle painter. And you can ask the style painter to use the style engine and say, style engine, draw me a combo box, given these options. And on my widget now appears what looks to be a well-drawn combo box. Then I go ahead and draw the combo box label on top of that. So to the end user, it looks like a regular combo box. But when they hit the button, they see a tree. And they don't realize it's a whole other widget. You can also use the style engine to influence a user experience. Because on the Macintosh and on some other platforms, on a spin box, these arrows aren't together. Maybe they're on different sides of each other. One on one side of the value, one on the other side of the value. Well, what you can do is you can use the style engine to tell you where objects are. There's this concept of a sub-element. So for our combo box, we need to find out where the button is that the user can press to pop down the tree. And that's actually pretty easy, because we make our options again. We tell, basically, the style engine our size, and that we have a button, and that we're editable. And we use a function from the style called hitTestComplexControl. So for this complex control, simply tell me which subcontrol my mouse is under. And if the style tells us that the mouse is under the arrow, then we either open or close the view based on its last state. So once again, this is all code that Trolltech, Nokia, has used to implement all of these widgets so they look unique on every platform, but they've exposed this functionality so that you can do this yourself. When I teach class and when I'm on consulting projects, a topic that is often right to the forefront is performance. How do we make sure that when we write our applications, that in the end, they're going to be fast? And what techniques can we use to make sure that we have to do as little profiling and rework at the end to make our application run as fast as possible? In fact, some of our engagements as consultants have been simply to come in, profile applications, and make them faster. So I'll share with you some of the pitfalls and things that you can use to make your thing faster. Now, I might sound like a college professor right now, but the best thing that you can do if you're a very data-intensive application is to use iterators and to avoid looking things up by index. It sounds very simple, but you'd be amazed how many programmers, just out of convenience, will just start writing for loops left and right to iterate over entire structures. And if you have linked lists that are very long, you're going to spend a lot of time just looking up pointer to pointer to pointer to find the 150th element. So the code does look more complex, especially junior programmers look at reverse STL iterators, and they don't know what's going on. They're afraid of them. But Qt has facilities that are going to help make fast loops. So one of these is the ability to dereference iterators. Like I said, most of the data classes are implicitly shared. Your data classes can be implicitly shared. So rather than having over and over again dereference I, dereference I, dereference I, you can actually copy that to an API that is your actual class. It helps with readability of code. Qt has their own container classes that are not part of the STL. Qt can actually be compiled entirely without STL support. However, the iterators that are used on those custom lists and hashes and maps are actually compatible with the STL iterators. So you can use algorithms from STL algorithms. And here's an example of iterating using STL iterators in forwards and then in reverse. Thing you should obviously know as a C++ programmer is that it's asymmetrical with C++. The first iterator actually has data at begin, end is invalid, and you should never access it. However, Java, being a much newer language, decided to rethink the iterator so that it would be symmetrical, that you would start on valid data and also end on valid data. Trolltech noticed this too, and back in Qt 4, they decided that they were going to add on new iterators that would be compatible with the custom Qt containers. And they implemented Java-like iterators. These have the Java syntax, where you can make an iterator, it's a template type, and say has next and previous, and you can iterate over your structure using next and previous in a symmetrical manner. So in Java, you have iterators, which are effectively const, and then you have mutable iterators that will allow you to actually manipulate the list without destroying iterators. So here's an example of going backwards through a list and removing every other item. And this will not destroy the iterator. If you need an easy syntax to iterate over an entire structure, an entire list, Qt makes this very easy because they provide an easy-to-use for each macro. There's actually one of these that comes with the STL as well, except for some reason takes in a data structure a begin and an end, which is a little, could be typo-prone. You might fence post over, and maybe not get the last item, things like that. In Qt, for each basically takes a temporary variable to copy into, and it takes the data structure. And what's going to happen here is that we're going to iterate over this entire list, and we're going to use a const reference to big data throughout our iterations. And using const references in the for each macro is the best way of doing things. Unless you're modifying the values, make them const references. Another question that people have is there are two different graphics classes for off-screen buffers in Qt. There is a QPixMap, and there is a QImage. And the question is, why are there two of them? Well, the answer is that QImage is a platform-independent, basically pixel buffer. It's an array of pixels. It lives in your application memory. So this is something that gets run on the main processor. It is in your application's address space. And it makes it very easy to say, we're going to go through this image and set every other pixel to red. However, since it's in your application's memory, to display it actually on the screen, you've got to copy it into system memory. It's got to get to the graphics card somehow. So when you actually draw a Q image, in the background, it's making something called a QPixMap and drawing the QPixMap to the screen. Because the QPixMap is a representation of a native bitmap. On X11, this is an XPixMap, which basically means it is nothing more than a glorified identifier to some memory out on the X server. That memory could even be located inside the graphics card. You also have no idea about the color space of this image either. It could be in native YUV or something. And when you draw to it using RGB colors, the X server is doing the conversion. So with QPixMap, you don't have the ability to do image manipulation. You can draw to it, because the X server can draw lines and draw rectangles. But you can't manipulate pixels. But it draws to the screen very quickly, because chances are, if you're drawing it a lot, it's already in graphics card memory. And all the X server has to do is call hardware memory copy. Boom, boom, straight to the screen, rather than having to transfer it from your application to the graphics card. Another performance tip is some of you may have used Q Network Access Manager, which is a fantastic class for downloading content from, say, web servers. I'm going to show you an example that downloads tiles from OpenStreetMap. And it makes it very easy, because you basically make these packets. They get processed asynchronously. You get the data back. It's going to handle making sure that the content is downloaded and you're notified when it's available. What some people don't know is that Q Network Access Manager can actually cache the files that you download to the disk. Some places that we've done consulting for, they've gone through great lengths to write their own data cacher, when they could have used one that was already implemented by Nokia and can simply be turned on inside of Network Access Manager. So you can say, Network Access Manager, from here on out, I would like you to prefer the cache. So if I ask you for a URL that I've already asked for, I'll get the cached version, and I won't spend any time re-downloading the data. The light maps example from Qt Labs, and that's at labs.qt.nokia.com, is a perfect example of this. So this is an example program that is used to show off some things with graphics view and GPS coordinates inside of the mobility classes of Qt. And it's very clean because it's an example program. They want to get across the key points, so I would suggest everybody go home and read it. And you'll notice that in the constructor, they make their Network Access Manager. This is going to be their oracle that they're going to ask for all this information. And immediately after making it, they make something called a Q Network Disk Cache. And we take this cache and we give it a path to save its files. You can even save files across runtimes. And then we set the cache on the manager. So if you don't expect your data to change that often, you could actually store these permanently to the disk. Then we do the usual with Network Access Manager, where we connect the finished signal to our slot to handle the network data. But in this case, those network transactions are going to happen very quickly. So like a simplified version of the request is we make a URL, basically where we want to go. And we make a network request, which is going to take the URL and the type of attribute that we want to use. So here, we are saying we're going to grab a hunk of user data, and we're passing that in as a variable called grab. And we append that to our list of impending replies, because we're going to need to resolve. We're sending all of these requests out asynchronously. They're going to come back asynchronously, and we need to make sure we keep a list so that we can say that this packet coming back is the one I've been waiting for. So using Network Access Manager can save you a lot of code, and it can also save you a lot of time and performance because you don't have to write your own cache. you can use the one that Nokia has written for you. So we're going to go through some kind of miscellaneous things. And some of these are going to sound pretty basic. You may have run across them before, but they're all good ideas. And if you haven't heard of them, now is as good a time as any. So the first is there's a special type of cast that you can use with QObject. And it's called QObject cast. And it looks and behaves exactly like dynamic cast, except it is library safe. On some platforms, if you dynamically cast things that are actually allocated by a library, dynamic cast can erroneously fail. And what this cast does, it does not use the real-time type information system from C++. That's what dynamic cast uses. In fact, you can build Qt entirely without RTTI. What it uses is that meta object information that we talked about slides ago. It has all the class names. It has all the information about inheritance. And it has the meta objects themselves. So a naive implementation of QObject cast could do string compares against the class names. Is this the same class name? And then do a static cast. In fact, that's what some older compilers used to do for dynamic cast. Pretty ugly. However, the actual implementation uses the meta object pointers. Because for every class that you instantiate, there's still only one meta object for that group of classes. It's static information. So QObject cast is as fast, relatively, as dynamic cast. You can use some interesting functions on QObjects to return you children, let's say. I have a dialog that's full of combo boxes, but they're inside of group boxes inside of that. But I need to set a property, or I need to get all the values from the combo boxes. I could either save off all their pointers individually and have one line of code for each value I need to get. Or I can use the findChildren template function. And this is a template function on QObject. And it has a templated return type, which is really cool, too. It uses built-in QObject cast. So you'll see here that we want a children of my own custom widget called myWidget. And we simply say, all right, I'm in a dialog. That's also a QWidget. We're going to say findChildren, everything that's a myWidget. And I found them all. You can also take that a step further. Because in Qt, you can give all of your objects instance names so that you can uniquely identify objects at runtime. So you don't just get a class name and a pointer. You can get an object that says, you know, this is the label for the font combo box. So you can actually pass a name that you're looking for to find children. So the second instance will only find one widget, and that's the myWidget that has a name called hi. So there's a couple easy ways to get from generics back into your actual subclasses. QComboBox has an interesting feature that I like to talk about when we do the basic class. And it's the ability to map a string to a hunk of data. Because your combo box you're presenting to the user is going to have a number of options in it. Do they want option 1, option 2, or option 3? Now, you know, back in Qt 3, before they had all of this stuff, you would have to, in your slot, when the index changed, you had to say, well, did they pick string 1? OK, that means this wants one object. Did they pick string 2? That's some other object. In Qt 4, add item takes an extra parameter. That's a Q variant. And it is called user data. So if you made a color combo box where they could pick red, blue, or green, you can add an item that is the text red and Q color with a value of red. And populate your combo box so that when the index changes, you already have a mapping of string value to actual data value. So here's a simple example of making a font combo box. We use the font database which you could use if you wanted to do this. There's also one that's pre-built in Qt for you. And we're going to go through all of the fonts, and we're going to add them to my combo box. And we're going to give it the family name. And we're going to give it an actual Q font instance. So later, inside of index changed, I only need one line of code, which is set font with the item data. Because at that point, we no longer care what the string was. Those of you here in Europe probably already know all about internationalization. This is really here for the San Francisco people. Us as Americans, unfortunately, think of translation as an after-the-fact thing. Oh, I'll write this program, and the translation group will figure it out. When in reality, it's way, way easier to start from the very beginning and wrap all your user-visible strings in TR, regardless of whether you initially intend on doing translation or not. It's 4 extra characters. It's not going to give you all carpal tunnel syndrome. But one thing to keep in mind is when concatenating strings. You'll notice that in this example here, where we say file plus file name saved in English, that makes sense. However, when the translator goes to translate that, they're not going to be able to move those words around, and other languages aren't going to be happy with that word arrangement. What you can use is a replacement mechanism in QString. QString allows you to embed these percent identifiers. And you can use %1 to %99. And it's going to do string replacement inside the string. And your translator can move around the percents in any order they want. Qt will make sure that the replacement is done in the correct order. So the replacement is done by using that arg function at the end of a QString. So that will replace %1 with a value. Another successive call to arg replaces %2. So it's a very basic tip, but it's amazing how projects go awry in the translation stage because there wasn't enough preparation. The next miscellaneous piece of advice I'd like to give is using designer-generated code. There's actually 3 or 4 different methods mentioned in the Qt Assistant documentation. People often ask, well, what's the best way? Why would you want to use the other 3? Well, the best way takes a little bit of extra work, but is the most reusable. You want to use a private pointer to the generated class. Why do we want a private pointer? That we have to make sure we have to delete and not make it on the stack. The reason is that you can use forward declarations. So if you subclass your designer code that has implemented this, if you need a subclass, you don't need to include a generated header file. This means you can take your class and now make a library out of it without having to depend on generated code. It also is going to offer you better flexibility and binary compatibility. Because your external interface only has 1 pointer, you can add, remove, change anything you want about the contents of that pointer, and you're not going to bomb anybody's application. There is one thing to mention, that you have to delete this pointer. It is not a Q object. It does not have a parent. It is actually a very simple data structure with one function called setupUI. And here's an example here. We are forward declaring calculator form, and we have a private member pointer called UI, instance of calculator form. So in our implementation, we make a new instance of calculator form, and we call setupUI, as you normally would, no matter how you use designer. You got to remember later in your destructor to delete that structure. And then you'll notice this header file is completely safe to ship in a library. You're not going to have to pound include UI underscore crazy name. And that brings us to the end of the sort of grab bag miscellaneous tips. Another topic everyone loves to talk about is threading. How to do it properly, how to do it efficiently, how to do it without, making spaghetti out of your application. So I'm going to share some things that you can do with threading in Qt, and hopefully make things a little bit easier. So some generic threading tips might be to use some classes that already use threading or already use background processing, such as Qt Network Access Manager. There's no reason to go ahead and create a thread pool for getting things from web servers when you simply can use Qt Network Access Manager. Likewise for Qt host info, sockets, and so on. If you are simply doing something where you want a parallelized for loop, where the data items are actually being manipulated independently, you can use a system called Qt concurrent, which is a parallelization mechanism in Qt. And there's an example of this on the next slide. Here we have a function that will scale an image. This is something that could take a very long time if we have a lot of images and they're very big images, especially if we want to do smooth transformations. So all this function does is return QImage's very own scaled function. Inside of main, we make a list of images. This could be quite long. It could be quite complex in its images. And all we do is we call a static function called Qt concurrent blocking mapped. And what this is going to do is it's going to process the scale function over each one of the items and images. And Qt concurrent is going to handle the thread pool, so it is going to maximize your processor set. So on a 8-core machine, it's going to launch upwards of 8 threads. And on a single-core machine, maybe it only does 1 or 2. But all of this is taken care of behind the scenes, so your application will be flexible no matter what type of hardware your customers may have. So of course, when you actually decide that I really need to use Qthread because Qt concurrent just isn't something I need because I'm not basically doing a glorified for loop, I need real work queues. Well, Qt makes it very easy to make work queues because each thread can have its own event loop. There's the main GUI event loop. Then if we kick off a thread and call exec, we have a whole other event loop. And Qt offers us this thing called cross-thread signals and slots, where instead of a signal immediately executing a slot, a signal connected to an object in another thread will create an event and post that event to the other thread's event loop. That event simply calls invoke method at some time later. It says, just run this function with these parameters and do it. And likewise, you can have signals and slots come back. Now, since Qt event loops are already mutex locked, you can use that as a work queue. You can send work pieces over signals and slots. You can get work products back over signals and slots. And you won't have to worry about maintaining your own work queue. So it's very easy. All you have to do is implement a Qthread that has a run function that all it does is call exec. And exec is just going to wait for events. And generally, threads don't normally get events. So it's going to sit there idle and do nothing. It is going to get events when it gets cross-thread signals and slots, though, and is going to wake up and process that work. There is one serious caveat when it comes to using cross-thread signals and slots. And it has to do with QObject thread affinity. What happens is that when you create an object in a thread, a QObject, it gets encoded into it the thread in which it was created. And it is going to use these thread pointers when it decides whether it's going to be a direct connection or a cross-thread connection. The QThread class itself belongs to the thread that created it, not the thread that it spawns. So if you connect signals and slots to it, they're probably not being run in the thread you think they're being run in. So the way around this is to use a worker proxy, where you create another object that is going to be created in the context of the spawned thread. And like here's an example of that. So here we're using two connects to send work and get work back. And here we are using our own signal work available, and it has a work type. As long as this is Q variant compatible, you can pass whatever data you want across cross-thread signals and slots. We have a pointer to our thread who has a member called worker. And we get a pointer to the worker, and it has a slot called doWork. Likewise, we connect to the worker's signal, work complete, and hook that up to our slot for done processing. This is because we cannot rely on connecting signals and slots to the QThread instance itself. And it also makes it really easy to dispatch work and to get work back. Because the dispatch work, all you need to do is emit work available whenever it's appropriate. Likewise, all you need to do to get the work back is to implement a slot. And here is just some code that is, the header file for the actual QThread that has a worker pointer. So if you do decide, now that we're inside of our own threads, we need to start locking things. So there's Q semaphores, there's Q mutexes. There's also Q read-write mutex, which is like a combination of semaphores and a mutex. There is a really nice convenience called Q mutex locker. This is a very simple class. It's actually kind of brilliant. What it does is it takes a mutex in its constructor, and its constructor simply locks the mutex. Then, when mutex locker falls off the stack at the end of the function, it goes out of scope, its destructor is called. And its destructor unlocks the mutex. This allows you to lock the mutex at the beginning of a function and have multiple returns anywhere you'd like them, whatever looks better for readability of your code, without having to worry about missing an unlock on one of your returns. Also, Qt supports an interesting feature called recursive mutexes. Sometimes, if you want to have your functions very short and clearly defined, sometimes you're going to need to have one function lock a mutex because it wants to change some data, but it also has to call another function, which also locks mutexes, because it also needs to change data. And generally with mutexes, you're not allowed to lock them twice, even inside of your own thread. But with the QMutex, on construction time, you can pass it the recursive parameter, so that you can make a recursive mutex that within the same thread, only the same thread, you can lock it multiple times. Just be sure to unlock it exactly the same amount of times that you have unlocked it. Well, locked it. So finally, our last section is actually a very general, broad topic, which is about testing and how, well, it should be built into your process. There should be unit testing. There should be functional testing. Things need to be checked. And Qt actually has a lot of facilities that are going to enable you to write your tests very easily, even for things like simulating mouse and key press events to test your custom widgets. So regression testing. Qt comes with its own regression testing library called QTest. And it allows you to write very short, easy-to-read tests. It is very similar in syntax to things like JUnit or CPP unit. It can simulate mouse and key events, and you can even test signals. Like a problem you may have in your testing with Qt is you have these classes that emit signals. And when you implement a class, you never really worry about if anybody's listening to these signals. It's loose coupling. However, when you're testing, you want to make sure that those signals are actually getting emitted when things change. QSignalSpy will let you do that. You could use a functional test product, like Froglog or Squish. They have a booth here, and it's basically full application testing. Well, it will record in the language of your choice all the key clicks that you use around your application to have a functional test of the end product, which is slightly different than unit testing. And there are tools available specifically for Qt. Also, you may notice if you read the source code to Qt, all over the place there are Q asserts, and there are Q assert X's. And these are asserts, just like regular asserts that are going to basically bomb your application. Never put any functional code into asserts. They are compiled out in a release mode binary. But in Qt, if you want a breakpoint when a QAssert is tripped, you can simply go ahead in your debugger and set a breakpoint on the function QAssert. And there's QAssertX. And usually by breakpointing on both of those, you can very easily track down where the assert is actually happening before it starts to bubble up. The QTest framework is very lightweight, very easy to use. It can test both regular C++, it doesn't need to be a Q object, doesn't need to be anything specific to Qt, and it can test widgets. So you can use it to test your whole application in unit tests. The macros are very similar to things you might see in other testing toolkits. You have verify, compare, skip. When things fail, you can have messages associated with them. That's what verify2 is for. If you want to test widgets, you have key click and key press. And the cool thing about these functions is that it's actually simulating the events inside of Qt. So you don't actually need to worry about, while my tests are running, I can't touch the mouse. You can actually run these tests and use your computer, because it's not actually moving the mouse around. It's simulating it inside of the Qt event loop. So here's an example of a test. This actually isn't a well-written test, because it tests more than one thing at a time. But it's just an overview of some of the things you can do. Like here, we have a line edit, and we send it some key clicks, and we verify that the text now appears in the line edit. We have a button, and the button has a signal called clicked that should be emitted on a mouse click. So we use a QSignalSpy to attach that signal. We create a mouse click, and then we ask the signal spy, OK, well, how many times did this get emitted? Well, sometimes you find bugs where, by accident, you've emitted a signal multiple times. You can also ask it about the arguments. Is this the correct signal? What is the signal name? So testing signal and slot connections can be a little troublesome. You may have noticed that signal and slot connections are not checked at compile time. They are checked at runtime. And Qt is nice enough to print out to the screen that a connect has failed. And in debug mode, it will try and give you help as to where it failed. However, you could be happily running your own unit tests in your own little library, and someone else who's using your library hasn't noticed that some of your signals have changed. And now their connections are failing. And unless you have a comprehensive set of unit tests, you may not find this until someone actually opens the dialog that the other person's writing. So there's a couple of things you can do. First of which is you could use the output of QTest or Squish, and you could grep it for bad signal and slot connections, because those are going to appear in the standard output of the tests. The other thing you can do is, if you want to have a broken signal and slot just simply crash in debug mode, you can use QAssert, because connect actually has a return type, a Boolean return type. And you can check this to find out if the connection actually worked. So here we are getting a value back from connect, and we're just asserting it on true. And that would bomb in debug mode, and we would know that our test crashed. We would get an email from our either testing department or automated tests. Bad things happened. You may notice a weird piece of extra code there called QUnused_OK. The one problem with using asserts and these variables is you will get a compiler warning that says unused variable in release mode. This is because QAssert gets entirely taken out of your application. But Qt comes with another macro that simply touches your variable with a little void star and becomes now used. Just to reiterate, make sure that you do not use QAssert with code that actually needs to get run. So you should not wrap connect in QAssert. So that brings us to the end of tips and tricks. I hope that there's been enough information here where some beginners learn some things. There might be some things for the more advanced folks. I'd like to thank you again for attending the session. I'll be here at the ICS booth if anyone wants to stop by. Like I said, I promised everybody notes. But I'd like to get in a few questions in the 3 minutes that we have left. So I think our room proctor was going to have a microphone. So if anybody has any questions on anything up here or anything at all, feel free to raise your hand.
Hello. I have a question referring to threads and QObjects. When I create a QObject in a separate thread and I connect it and the thread gets destructed, what happens to the connections? Or, sorry, a better question is, there's a function called move to thread in a QObject, and what happens to the connections? When I use, for example, an auto connection to a slot from the main thread, from an object to a main thread, something like that.
So that is a good question. When do the connections get resolved in auto type? So there's the auto connection. It will automatically decide whether or not it's a direct connection or a queued connection. And the answer is they're actually checked at runtime when the emission happens. So if you make a connection, and that would be a direct connection on AutoConnect, and then you move that object to a different thread, the next time that connection is invoked, it becomes, at runtime, a queued connection. Well, I'd like to thank you all again for coming, and I suppose everyone can try and get a good seat for the next round of talks. I'll see you out at the ICS booth.